So this is going to be the first half of a two-parts talk. The second half will be done by Alessandro Monguzzi, and I'm going to report on a joint research project that we started, and well, I will report on the results that we have so far. So let me set up some notation first. Well, describe the problem. Please tell me if there is any problem with the audio or anything. Okay. And the problem is the p-boundedness problem for Bergman projection. So I guess I can be quite rapid on the statement. And the problem is, in its more ambitious version and probably impossibly hard in general, is to determine, well, given a domain. And my domains in this talk will all be bounded. So given a bounded domain in Cn, determine the values between 1 and infinity, such that the Bergman projection which I'm going to denote PD, which of course is defined on L2 of D. L2 is always with respect to the Lebesgue measure, onto the Bergman space, which is the intersection of L2 with homomorphic functions, and so to determine all the values of P such that the Bergman projection is LP bounded. And this is a rapid way of saying that the operator, which is initially defined on L2, admits a bounded extension to LP, or equivalently that you have the following a priori estimates, where dm is Lebesgue measure. And
sorry, I tried to mute somebody and then I think I muted you.
No problem, no problem. Okay. Yeah. And then, okay, this is the a priori estimate that guarantees the extension, and this is what you want to prove. PD a priori is defined only on square integral function. And then, of course, this is a very ambitious problem, and it has been studied for many classes of domain, most notably for smooth pseudo-convex domains in various classes. But I want to focus in this talk on domains that are singular of various kind. And I will say something that there has been some amount of work by other people also, of course. But let me, before that, just state as a vague classification of the kind of results that you can hope for. This one possible way that one can think about possible results, or the way we think about there are sharp results. By sharp I mean that you're able to fully characterize the set of P's for which you have boundedness. And it's well known that by standard interpolation and duality argument, this set of P's is an interval, and it has a symmetry property. More precisely, the set of 1 over P's is in the interval 0, 1. The reciprocal of the exponents is symmetric with respect to the midpoint 1/2. This is a consequence of self-adjointness of the projection. And so the goal is to characterize this. And if you're able to do that completely, so to fully determine the set of P's, then you have, let's say, a very sharp result. But also non-sharp results could be interesting when you have no way or you don't know how to determine to get sharp results. And you can think of two kinds, at least, of non-sharp results. And these are regularity results, where you probably don't know if all the set of P's for which you're not able to characterize completely the set of P's for which you have boundedness, but you can at least prove that in some non-trivial interval around the value P equal to 2, you got boundedness, okay? And then there are non-sharp irregularity results. And non-sharp irregularity, I mean that you're able to exhibit a P to say that at least for some finite value of P, or equivalently for some value of P larger than 1 by duality, you have unboundedness on the corresponding LP space. Let me say concerning this that one usually, from the beginning, already thinks that in terms of the goal of determining the set of values of P strictly between 1 and infinity for which you have boundedness, somehow because you already automatically expect that you have unboundedness for P equal to 1. But I'll take the occasion of speaking to an audience of experts to ask if anybody has a proof for general bounded domains that the Bergman projection is automatically unbounded on L1. I don't know of any counterexamples unless I missed something, and I tried to prove that, but I was able to prove it only for domains with some degree of smoothness. Okay, anyway, one expects that one has unboundedness on L1, and so typically when one thinks of irregularity, one really wants some value of P, say strictly between 1 and 2, for which you don't have this a priori estimate, and the Bergman projection is unbounded. Okay, and of course the worm is an example for which you have an irregularity result, and we know nothing about positive regularity results, the smooth worm. And now I'm gonna try to do this. Okay, and the goal of this talk in short is to try to establish mostly non-sharp results. And then Alessandro will talk about sharp results for domains that exhibit singularities. And the way we're gonna do this is to exploit the existence of ramified coverings. So first of all, I have to recall very rapidly what I mean by ramified covering. Well, first of all, let me say that ramified covering is a nice geometric expression. It's very expressive, but it's used in various contexts. Now I'm talking about domains in Cn, so let me be precise. And one could argue that there could be different names. I'm not claiming that this is absolutely standard, but what I mean, more importantly, is this. I got a domain D, and this is the one for which I want to understand the behavior of the Bergman projection. And on top of that, I got another domain E. Okay. And before telling you what is a ramified covering, let me recall what a covering is. Of course, probably all of you already know that, but by covering, just to set up notation, I mean a map in pi, and E and D, remember, are domains in Cn, and I want the map in pi to be holomorphic. This is always the case in this talk, even though, of course, coverings exist in the topological category and they have a nice topological theory. And what is a covering? A covering is a map in pi with the property that when you pick a point P on the base space, D in this case, then you're able to find an open neighborhood around P with the property that its inverse image with respect to pi is the disjoint union of a number of connected pieces. There will be Q of them, and I'm thinking that Q is finite. Of course, there are coverings with infinitely many sheets, but these are finitely sheeted coverings. This is always be the case for me. And Q is the multiplicity. Okay. And you also want that when you restrict pi to each of these pieces, this induces a homeomorphism in the topological category. And here we want a biholomorphism. Okay. And so this is a covering, but we want to allow ramifications. So what is a ramification? Well, this is not, this is simple to state, because this is just a covering where you actually have a covering, but after you remove something, the ramification locus from, say, the base space. So I want to think that I'm removing V, where V is some thin set, which I'm going to precise in a moment, and you correspondingly remove something on the space on top. And actually, what you really want is an ordinary covering. So pi is now a covering, but between these two spaces. And one may use this dash notation to mean, well, actually, the covering is only defined outside a ramification locus. Okay? Well, actually, since this is holomorphic and I'm thinking of bounded domains, after I tell you what I mean by thin sets, automatically pi will extend to the whole of E, but this doesn't mean that the extension maps into D. It could map into the closure. So it's better to think that pi is really defined only outside of the ramification locus. And here I mean that by thin, I mean that V and W are proper analytic subsets. Okay? So these are sets that are locally defined by the vanishing of a finite number of non-identically zero holomorphic functions. And so being analytic sets, as I said, you have Riemann extension removability of singularity for bounded holomorphic functions. And as I said, pi automatically extend to the whole of E, but really defines a covering only outside the ramification locus. I'll give examples in a moment. But the next step when you study covering, and this is already true, of course, in the topological category, it's good to study nice coverings, which go under various names in the literature, normal, regular, or Galois sometimes. But what this means is that there is a nice symmetry group acting on the covering. And to define that, I want to introduce the group of the covering, okay? Which when pi is clear from the context, I just write G. What is G? G is the set of automorphisms of the space above E. And here, automorphism means, again, bilomorphisms, okay? The holomorphic category, and which satisfy this property. Pi GZ is equal to pi Z for every Z in E. What this means is that each point on E is only allowed to be sent by the automorphism to another point on the fiber over a given point. So this is automatically finite group, and this is what's called sometimes in the topological textbooks the Tek transformation group. Okay, and here comes the key definition. The ramified covering pi is normal, as I said, sometimes Galois or regular, if the covering group acts transitively on fibers. So, as I said, the group maps shuffles these leaves that you see locally over a point. And what this means is that you give me 2 points on the fiber, then there is an element of the group which maps one into the other. Okay, if this happens, then the order of the group, G is a finite group, its cardinality is exactly equal to Q, the multiplicity of the covering, of the ramified covering. Okay, normal coverings are the nice ones for which one can say a lot more, and I only work from now on with normal coverings. And now it's time to give some examples, but let me recall my goal. My goal is to try to study LP boundedness of Bergman projections on a domain whenever I know that there is a ramified covering, and maybe the space above is nicer than D. Vice versa, when you start with a map in E, typically a ramified covering may create singularities. This is what typically happens, even though E is very nice and smooth, or has certain kinds of singularities, typically D has stronger singularities. And what are the examples that I want to discuss? Of course, I'll be rather sketchy, since this is just a 25 minutes talk, but let me try to give you examples of these situations. I give 2 classes of examples, actually. The first class, in the first class, I will start with the covering pi, and then I will say something about the covering group. And in the second example, I will start with the group and build coverings with this group as groups of as covering group. So the first are called monomial maps, and this you should compare the literature with a very nice paper by Nagel and Pramanik from 2020, and also I hope to remember all the names, a paper by Bender, Chakrabarty, Edholm, Mankar from, I guess, also 2020, where these domains appear. In particular, Bender, Chakrabarty, Edholm, Mankar actually use this kind of strategy to prove sharp results about the p-boundedness of special domains where you have as covering maps, monomial maps. But let me discuss the situation in general. What is a monomial map? Well, you start with the matrix, and I'm going to assume that the matrix has natural numbers as entries. There is a corresponding theory more general for, well, you can think of matrices with integer entries, but then there are some complications, and these are discussed well in both papers, but let me think of natural numbers entries. So these are ordinary monomials, okay? And there is the key assumption that the determinant of the matrix is different from 0. And now we got a matrix with natural number entries, and each row you may think as a multi-index. So if you use this as a multi-index, you produce n monomials. And so you have a map in pi, which depends on the matrix, which sends an n-tuple of complex numbers to the corresponding monomials, right? You use, for example, the first row to build the monomial, and so on, the second row for a second monomial, and the nth row for the nth monomial. So you got a mapping from Cn to Cn, and actually as a consequence of the non-singularity, this is shown, for example, in Nagel-Pramanik paper, that pi A induces a nice ramified covering on the full Cn, for example, okay? And pi A induces a ramified covering, well, actually on Cn, but also more generally on E, any bounded domain, bounded G pi A invariant domain. So what is the covering group in this case? Well, you can compute. There is a nice discussion again in Nagel-Pramanik paper. Now, I don't have time to write down all the definitions, but let me say that this group, in this case, this is an abelian group. It's a nice group, a subgroup of the unitary group, where you are allowed to rotate by a certain root of unity each of the coordinates, but then there are certain constraints which come out naturally from the definition of the monomial map. So that may be rather sketchy, but let me say that you already find very interesting examples where the covering group is abelian, and I refer to this paper for discussion of LP boundedness for a very special choice of a bounded G-invariant domain, which is the polydisk. And this gives rise to many interesting singular domains, in particular the Hartogs triangles and various huge generalizations of those, which I think they call monomial polyhedrons, okay? And this is a class, okay? And these are all abelian, already quite complicated, but since we are working in this general setting, let me at least advertise that you can try to think about interesting examples where the covering group is non-abelian. And this is what I want to say now. Okay. Of course, please stop me if there are questions. And what are the non-abelian examples I have in mind? Well, I want to consider a class of groups this time. As I've said before, I started with a covering map, and then I said something about the abelian. Well, I told you that there is an abelian covering group, but here I will start with the groups. So what is the class of groups I'm interested in? These are the reflection groups, okay? Well, what are reflection groups? Well, these are subgroups of the unitary groups, UN. So again, linear groups, unitary groups, as before. But in this case, the definition of reflection, it means that this group is finite and generated by, of course, a finite number of elements of UN that are reflections. So I should tell you what is a reflection. And a reflection is just something that in some basis, orthonormal basis of Cn, have this representation, alpha, 1, 1. Okay, this means that this is a diagonal matrix with n-1 eigenvalues equal to 1, and alpha, which is some cute root of unity, where alpha is not 1. So the matrix should not be the identity. And for example, if alpha is -1, this is the ordinary notion of real reflection, okay, where you have a fixed hyperplane and you reflect. But this is in the complex setting, you may allow a cute root of unity. And this is a reflection group. And there is a beautiful theory of reflection groups, somehow generalizing the one available for for complex reflection groups, generalizing the theory of real reflection groups. And this goes under the names of Chevalier, Shepard, and Todd. And what's the only consequence that I want to recall of this theory that is important for us is that, if you look at the ring of invariance of these groups, so if you look at the polynomials in m variables, which are invariant under the action of the group, which by a well-known theorem of Hilbert is finitely generated as an algebra. This is actually polynomial algebra generated by n basic invariants, okay? And the crucial fact is that the number of generators is equal to the dimension. And this is the key property which also defines actually, this is a non-trivial theorem, characterizes reflection groups, okay, where these are homogeneous generators. So these are M polynomials which are G invariant. And this is a huge generalization of the familiar theorem that symmetric polynomials that are invariant under the symmetric group are polynomials in the basic symmetric functions. And what do I want to do with that? Well, I want to build a ramified covering whose components are the n mapping, the n functions q1, qn, and this induces a ramified covering on, again, on any bounded G invariant domain. So this means that you can play around with these groups and produce a lot of ramified coverings. Let me make things more concrete with first a few examples. Well, the first example I want to consider is an example which actually falls into both the category of reflection groups and the previous one that I described of monomial maps, because in this case, I'm going to take as a group, this group, the group of diagonal matrices, which are unitary. So this just means that each element in the diagonal is a complex number of modulus 1, but then I'm requiring that each entry is a root of unity of a certain specific order. So I'm fixing M1, Mn, and I want all of them to be roots of unity. And of course, this as a group is abelian, and it's also a direct product of, or a direct sum of cyclic groups. Okay. And it's also very easy to see what is the ring of invariance. To be invariant under this just means that you are actually a polynomial in Z1 to the M1, Zn to the Mn. So what I'm saying is that natural choice of Q1, Qn in this case is Z1 to the M1, Zn to the Mn, okay? And then you have to choose your favorite bounded invariant domain with respect to this group. So for example, you may choose the ball, Bn, this is the unit ball in Cn, and look at its image. And I claim this is a ramified covering. And more importantly for us, well, what is the domain that you get? Well, it's very easy to think a moment about that, and you see that the domain is this one. And this kind of domains were studied in the 80s, I think, by Bécollet, and he actually proved that even though these domains are singular, they're quite nasty cuspidal singularities. The Bergman projection is bounded on LP in the full range, at least in dimension 2, and also for, well, there are some further restrictions, but there are more general exponents. But anyway, he was able to prove in 2 dimensions that the Bergman projection is bounded on LP on the full range between P between 1 and infinity, okay? And this is a theorem we generalized in this setting with Alessandro. He's gonna talk about this later, but let me give you more context. This was again abelian, so I want to give you a genuine non-abelian examples. I guess I have, how much, 2 minutes, 3 minutes, I don't know.
You have 5.
Great, okay, thank you very much. Okay, so let me just give another example. In this example, I'm giving you the ramified covering again. We're in 2 variables, and this is the example. Very simple to write down. And it turns out that if you fix natural number m, and you look at these 2 polynomials, these are the generators of the ring of invariant of a very special reflection group. So, and if you look at this example, we have a theorem. This is another result that will be discussed in detail by Alessandro. And we are able to prove in this case, for example, that when you look at pi, the image under this pi of the 2-dimensional unit ball, the Bergman projection on this domain is LP bounded, for example, for any p between 1 and infinity. And this is a class of examples for which we were able to work out our approach, but I guess the methods that I will start to discuss now and Alessandro will develop are more general, but this is just to say that we're able to deal with a family of examples which is the associated group is non-abelian, and the geometry is quite interesting actually, and I didn't put the restriction, and this is our restriction if m is a power of 2. You'll see later where this restriction comes. And this is very interesting because in the boundary of these domains, there are singularities which have a very interesting geometric structure. In a very nice paper of Rudin, where he classifies proper holomorphic mappings with domain de Ball, he describes the case m equal to 3, and he shows that there is a singularity along a Mobius band on the boundary. So very interesting geometry, and still, even though there is quite a serious singularity, there is LP boundedness in the full range. So this is another example of a sharp result. But now let me discuss what are our methods, okay? So the basic tool, and just the start of our analysis is the lifting procedure. Of course, there is a covering, and the idea is to lift the problem from the base, which is the singular difficult domain, to the space above, okay? And let me give you this statement as a proposition. And this lifting procedure is a quite simple corollary of deeper results by Bell, going back to the beginning of the 80s. And again, this kind of results was exploited by Bender, Chakrabarty, Adam, Minkar in their paper. And I should have said that at the beginning, the initial idea, at least for us, was inspired by a paper by Chen, Krantz, and Yuan, where they use, in a very specific instance, this kind of procedure. And this is the right, I think, generalization of this approach. And it goes like this. You assume that you have pi, as I said, the ramified covering. This is a ramified covering. And I assume that it is normal, okay, with group G, okay? And the following are equivalent. The first is the Bergman projection on the base domain D is LP bounded. Okay. Well, the second statement is that there is a boundedness statement above, and this is the lifting. And the boundedness is the following. If you consider the function W, which is the complex Jacobian of the projection to the power 2 minus P, then you have the following LP bound. Write it and then I comment on it. And what is this bound? Well, first of all, this is a weighted bound. This is an LP bound, but with a weight, and a quite singular weight, because the Jacobian will in general, be vanishing because of the ramified nature of the covering. But more importantly, this bound should hold for every function u, not for every function u in L2, but only for those functions u in L2 which satisfy a skewness property. What does it mean to be skew? Well, this has to do with the group, and I hope you're able to read. I'm going to write the definition of skew here, and this means that u gz times the determinant of G is equal to uz for every element of the group. Okay, and so this is just a subclass of the group. Now I see that my time is over, so it's difficult to go through. But I got to the point where I wanted to arrive. Let me just comment 1 minute of one kind of non-sharp result that you can get using this method, okay? So this tells you that your LP boundedness desired result is a weighted estimate, okay? And now, for example, there is a cheap approach, let's say, to the problem, which is not gonna give you the sharp result in general, which is to ignore the algebraic structure. So to forget that you have a restriction on this, because if you just want to prove boundedness, well, it's enough to try to prove this estimate for every u in L2, and this is a weighted estimate. And you can use techniques from weighted singular integral theory to try to establish that your weight is in a Mukhenhaupt class. Okay, there are more refined results, of course, by Bécollet, as you know very well, but to prove LP boundedness, it's enough to establish, for example, that these weights are in AP. And in most cases, they are, because these are holomorphic functions. and there is a way to establish that. So there is an approach, this I'm just suggesting a direction that we explored a bit, to prove non-sharp results using just a cheap approach, forgetting the algebraic structure. And let me just close by saying that Alessandro's talk will exactly be about what happens when you take into account more carefully the algebra behind, and you're able to prove sharp results. So sorry if I delayed a bit, and thank you very much.